Okay, so let's talk about integration for our functions of several variables. Um, so, right. So first, let's take a step back to single variable calculus. So what is integration? So the simplest interpretation is just as the opposite of the derivative. So for y equals f of x, for example, if you know that f prime of x equals 2x, you can say find f of x. And then f of x is just the integral of f prime. So in this case, is the integral of 2x dx, and that gives you x squared plus c. And then if you know an initial condition, you can solve for that constant. So if you're told that f of 0 equals 1, you plug that in, you get, in this case, 0 squared plus c equals 1, therefore c equals 1. So your original function in total, f of x equals x squared plus 1. Okay, so that is a very quick review of one way to do integration. Now, how do we do this for our functions of two variables? So let's take a look. Suppose that we know that f sub xy equals x squared y minus 4xy cubed, and then we're being asked to find f. And for now, we're going to assume all constants of integration are 0. I'll talk about that later. So we have to undo the derivatives. So this one is f derivative with respect to x and derivative with respect to y. So let's just follow the notation and undo the derivatives in that order. So first, undoing the derivative with respect to y. So we're going to integrate our function f sub xy dy, and that's going to give us just f sub x. So integrating this dy, now when we integrate dy, how do we do it? As you can imagine, just like with derivatives, treat x as a constant, and y is your only variable. So that's going to give you 1/2 x squared y squared minus xy to the 4th. And there's fx. And now we got to find f. So we integrate with respect to x, and now, of course, we treat y as a constant. So doing that out, you get 1/6 x cubed y squared minus 1/2 x squared y to the 4th. And there's your f. Okay. Yeah, we're going to come back to dealing with those constants of integration. For now, we're just going to take them to be 0. Okay. So this is, in this case, we really went slowly step by step, assuming, well, let's do this one integral first, and let's do this other integral first. We can, just like where we can write multiple derivatives in a single expression, we can again write multiple integrals in a single expression. And we can also, as we know that we can do with integrals, include boundary values. So let's take a look at just how that calculation would look like. So here we've got this integral, and so what do? So it's important to understand the way that we interpret this is that there's an inside integral and an outside integral. So first we've got the integral of 6xy squared dx, where x goes from 1 to 3. That's your inside integral. So no one ever writes the parentheses, but you interpret the integral as if they're there. All right. So let's go ahead and do it. So this integral, so integrate that dx, and you get 3x squared y squared, and then you evaluate it as x goes from 1 to 3. So notice that I'm writing x equals 1 to x equals 3 because now we've got several variables, and that's a notation that helps us keep track of, or reminds us which variable we're plugging in values for. Okay. So plugging that in, plugging in x equals 3, you get 27y squared. Plugging in x equals 1, you get 3y squared. And then subtract 24y squared. And now we're doing the outer integral from 2 to 4, 24y squared dy. So integrate that, you get 8y cubed. Evaluate y goes from 2 to 4. Plug it in, you get 512 minus 64, and you get 448. So this is, very quickly, what it means to do a multiple integral. So if we imagine that we're starting with this thing where we've taken both partial derivatives, we integrate back and we get the original function. And we can also integrate in either order, just like we can take derivatives in either order. And then we've also got boundary values if there are boundary values or if the problem calls for it. So I just want to check in if there are any questions. Okay. Sounds good. Let's keep rolling. All right. So we did this for z equals f of x, y. We can keep going and apply this to a function of 3 variables. So briefly, suppose we know that f sub x, y, z with all those partial derivatives is x squared y plus e to the x cos z plus y, z to the 3 halves. Find your original function f of x, y, z, and again, just assuming all constants of integration are 0. So what do? We have to do 3 integrals. First, we integrate with respect to z to get f sub x, y. So that's the integral of that whole function, dz. And when you integrate that with respect to z, remember that means we treat x and y like constants. So you get x squared yz plus e to the x sine z plus 2/5 y z to the 5 halves. So now we've got f sub x, y. Next, we integrate with respect to y. There we go. And that'll give us f sub x. So integrating that whole function gives us 1/2 x squared y squared z plus e to the x y sine z plus 1/5 y squared z to the 5 halves. And now we got to integrate one more time with respect to x now to get back to f. So the integral of that whole thing, dx, gives us 1/6 x cubed y squared z plus e to the x y sine z plus 1/5 x y squared z to the 5 halves. So it's the exact same thing. There's just basically more of it. And then, of course, you can also do this whole thing, including boundary values. So what would that look like? Let's take a look. Ooh, okay. Oy. Sorry, little tech issue. Hold on. Okay. So the first thing we have to do is we have to do that inside dz integral. So integrating that with respect to z, that's z to the 1/2. So we're just going to get 2/3 x z to the 3 halves plus z. And then z goes from 9 to 36. And we're going to hold on to those outside integrals dy dx. Okay. So now you plug in and you get 2/3 x 36 to the 3 halves plus 36 minus 2/3 x 9 to the 3 halves plus 9. So all that business, still holding on to those outer integrals. So if you work out the algebra really quickly, you get 144x minus 39. Sorry, minus 18x plus 9 dy dx. Okay? Simplifying, that's going to give us, sorry, that's plus 36. Okay. So 144x plus 36 minus 18x plus 9. Working that out, that gives us integral from -2 to 4, integral from 3 to 5, 126x plus 27 dy dx. And now we just do the same thing all again. So I'm just giving you a feel for what these calculations are going to look like. So now we integrate this dy. So 126 xy plus 27y, and then we're plugging in y goes from 3 to 5. Still holding on to that outer integral. One 26x times 5 plus 27 times 5 minus 126x times 3 plus 27 times 3 dx. Working out the algebra, 252x plus 54 dx. And now we can close it out in pretty quick fashion from here. 126x squared plus 54x. X goes from -2 to 4. So you get 126 4 squared plus 54 times 4 minus 126 -2 squared plus 54 -2. Work that all out, do the arithmetic, and you get 1836. So that's just a walkthrough of what one of these problems looks like. Okay. So that is what multiple integrals could look like for functions of several variables. And that was just how to do the calculation. So of course we can do this we did it with 2 variables or with 3 variables. We can do this in any way we like, any number of variables. So what we're gonna do right now that we know how to do the calculation, we're gonna look at what are some possible meanings and uses. Okay. So the first thing is to remember our basic use of integration for single variable functions. So when you have y equals f of x, we saw that we could approximate the area by taking rectangles where each width was some delta x, where that delta x was a piece of the interval over which we're interested. And then we take a point xi in each interval, and then we take f of that point to get to sort out the height of the rectangle. And then so the area of each rectangle is f of xi times delta x. And then the total approximate area is the sum of those. So the sum of f of xi times delta x. And then we get the exact area by taking delta x going to 0. It becomes a better and better approximation until we get the exact area, which is the integral. So the area equals the integral from a to b, f of x dx. So that is all from single variable calculus. Now, let's look at what we have for functions of 2 variables. So if we find the quote unquote space under the function, what does that space represent? Well, it's a 3-dimensional thing, so that we call that the volume. And we can find the volume using an integral. And there are two ways to think about this. Both of them are actually going to be important for us. So I'm going to show you both concepts. So the first way to think about it. So here are some pictures. So first of all, imagine that we want, so here's it. So in blue, there's our functions equals f of x, y. And then R is the region over which we're interested. We want to say, what is the volume over that region under our surface? So what do? We need to break up our region. And how do we break it up? We break it up into the objects for which we know the area in the easiest way, and those are rectangles. So we've got all these little rectangles, and I'm going to call each one ij. So some ijth rectangle. So in the image, you see it's set off by, it's right there. Okay. So then what do? So over that, we then make the three-dimensional object, which we know the volume the easiest, and that's a rectangular solid. So that's an approximation of the volume just over that little piece of the domain. And then over here in the bottom left, you see the all the rectangular solids put together, and that's an approximation of the volume under the entire surface. Okay, so how do we turn that into a formula? So here we go. So we're going to call the little rectangle, the little piece of the region in the domain, that's a little bit of area. So we're going to call that delta A, like a little change in area. Okay. So, and there's a point in there, xi, yj, and then the height that we're going to use for the rectangular solid over that little bit is f of that point, so f of xi, yj. So the volume over that small region is f of xi, yj, there's the height, times delta A, there's the area of the base. So the total volume, we have to add all those up. Now, how do we add those up? We add those up by taking the sum over I, which gives us over all the x values, and also the sum over j, which gives us over all the possible y values. And so there's the approximation we can write down as this sum. So the exact volume, how do we get the exact volume? By getting better and better approximations. We take delta A as it gets smaller and smaller and smaller. Now, calculating the limit exactly is hard. We won't do it, but we define that limit as a double integral. So the volume equals the double integral. Now notice this notation: the double integral over the region of my function f of x, y, dA. So remember that when we move from discrete or approximate things which use deltas, when we move to exact things, we use d's. Okay, so important comment here. dA, so previously we worked with dx and dy. dA, remember that it is a small area, so that is actually a two-dimensional thing. So that is a brand new thing. So we're going to learn how to calculate with it, how to use it, how to interpret it coming up. Right now, I just want to give you sort of the notational sense of what's going on. All right. So that's the first way to think about it. We think about breaking up the domain, like in the graph in the picture here, into tiny little rectangles. There's another way to do it. Let's take a look at that right now. So here's a different graph and different volume we want to break up. So let's think of this volume that we want to find as a stack of slices. So each slice at a different y value. Okay. So, oops, I was right the first time, sorry. So there's my y-axis. Great. Okay, so here's my y-axis. Here's my x-axis. And notice that each slice, we see the front of a slice right there. Each slice is at a different y value. So at each slice, the area is a function of whatever y value I've got. So let's call the different y values. Let's say there's a bunch of y values. Let's call them yj. And the width of each slice is delta y. So the volume of each slice is its area, area of a of yj times delta y. So there's delta y is the width, and then a of yj is the area. So the total volume approximated by summing over j, a of yj times delta y. But now we just said the area is some area function. How do we find area? So on an individual slice, we know how to find area. We take this and we approximate it with rectangles. And where this width was delta y, this width is now delta x. So on any rectangle, the height is f of the point, so f of xi yj, and the width is delta x. The approximate area of one rectangle is the sum of that. The sum over I xi of f of xi yj times delta x. So the approximate volume altogether, go back to what we had, the sum over j of a of yj times delta y, but we now have an expression for that and plug it in. It's the sum over j, times this thing that we just figured out, the sum over I, or of the sum over I, f of xi yj times delta x, and then all that plugged back in times delta y. And again, we know there's an approximation, and we understand how to convert this into an integral to make an exact statement. So the volume is just the integral of the area of y dy, but we know that we can replace with another integral. So this just winds up being the integral of f of xy dx, all of that dy. And as I mentioned before, when we were talking about just the calculations, as a tradition, we don't write the brackets, but we understand that they're there. So we get that volume equals the double integral of f of xy dx dy. Also, let's note that we could have first sliced, instead of along constant y values, constant x values. And that would switch the order of x and y. So that gives us the double integral of f of xy dy dx. And of course, the boundaries of integration depend on whatever information we're given about x and y. So for example, if the region is a rectangle over which we're integrating, and suppose that we know that x is between a and b and y is between c and d, then those are your boundaries of integration. So in that case, the volume is the integral from c to d, the integral from a to b, f of xy dx dy. And of course, again, remember to match the proper boundaries with the proper variable. Think in terms of inside function, or inside integral and outside integral. Okay, so let's see how this works. Let's do a problem. Okay, so here's a function, f of xy equals 2xy. Let's find the volume under that over the region enclosed by x equals 1, x equals 3, y equals 2, y equals 5. So what do? We just say the volume equals, now again, note that as we mentioned, it doesn't matter, at the moment, it doesn't matter which way we set up the integral. So I'm going to set it up in the following way. Integral from 2 to 5, integral from 1 to 3. Here's my function 2xy, integrating dx dy. So x is going from 1 to 3, y is going from 2 to 5. But again, we could have done it the other way. So what do? So now that we've set up the volume as the double integral, now we just calculate the double integral. So first we do the inside integral. Inside integral says integrate with respect to x. So that gives x squared y. And we need to evaluate as x goes from 1 to 3. So when we do that, plugging in x equals 3, you get 3 squared y. And plugging in x equals 1, you get 1 squared y. All of that dy. And then simplifying with the algebra, that just gives you 8y dy. By doing this integral, 4y squared. Y goes from 2 to 5. So 4, 5 squared minus 4, 2 squared. Work it all out, and you get 84. I always like to use units here to indicate what I found. This was a volume. So, for example, the units could be meters cubed. So just to show how it would go, yes, you could also do it in the other order. Okay. You can also set the, so our first integral was dx dy. Here we can set up the integral dy dx. So just pay attention to the fact that the boundaries need to match with the variables. So doing it this way, so the first integral, we integrate first dy, so that's going to be x y squared. And you evaluate as y goes from 2 to 5, we hold the dx. Okay, so plugging this in, so plugging in 5, we're going to get 5 squared x, then minus 2 squared x. And then simplifying, that's just going to be the integral from 1 to 3 of 21x dx. And then integrating, you get 21 over 2 x squared. Plugging in, x goes from 1 to 3. So plugging in 3 like this, then plugging in 1 like this. Work it out, do the arithmetic, and you get 84. And we can hold on to the meters cubed if we like. There was no units in the original problem, but I like to sometimes include units, and I use standard units. Okay, so anyway, the point of this is to show that yes, in this case, it's very clear how to swap the dx and the dy, which we refer to as the order of integration. We can switch the order of integration, just make sure that the boundaries get carried along with the proper variable. Okay. So that is the basic calculation or basic application of how you can use it, for example, to find volume for z equals f of xy over a given region. Now, next. So now we enter a new situation. What if the region is not a rectangle? If the region is not a rectangle, notice that the boundaries are not constants. And in particular, the boundaries of the inner integral must be variable depending on the outer variable. So let's do an example to show why this is true and what's going on. Okay, so here's the question. Find the volume under this function, f of xy equals 4x squared plus y cubed plus 4xy squared, and over the region enclosed by, and then we've got some formulas here. Y equals x squared, y equals 0, x equals 2. All right. So what is going on in this scenario? The first thing we should do that will always help us is let's have a graph of the region, of the situation. So I'm going to use computer graphics because that's helpful here because I want to show you everything. So notice that in one case, we've got the XY plane on the bottom, and you can see the domain, the region in the domain. And then I've also graphed the function as it sits over that specific region. So notice that we've got the curve y equals 0. That's here. Oops. Oh, come on. Sorry, one sec. Oh, man. There we go. Sorry. Okay. So notice that we've got on the bottom y equals 0, and then on the right side x equals 2, and then curving over there in the back y equals x squared. So it gives us this funky sort of like crescent triangle type shape region. So first of all, notice that all the possible y values are from, all the possible x values are from 0 to 2. All the possible y values go from 0, and then if you think about it, it goes to 0 up to 4. We'll figure that out in a sec. So actually, let's accompany this. Let me do this clearly. Let me accompany this with a little sketch, just in the xy plane. So y equals x squared looks like that. Y equals 0 looks like that. And then let's say x equals 2 is right there. So just from drawing this out, and my drawing wasn't amazing, you can see that this point is going to be when x equals 2, y equals 4. Okay. So notice that all x values range from 0 to 2. Let me label my region R. And then all y values range from 0 to 4. However, we cannot say that the boundaries of integration are x goes from 0 to 2 and y goes from 0 to 4, because if we said that, then that would mean that our region would be the whole rectangle, which is clearly not our region. So we have to sort out what are our boundaries. So now we go back to the sort of the second interpretation of how do we make a double integral to determine volume. So we make our slices. Now, before I showed you how to make slices, but I used a 3-dimensional rendering of the volume and of the function. You don't have to do the same thing. The only thing that you'll need is the 2-dimensional version, and that's what I've graphed on the, that's what I drew by hand on the right. So this is what we're going to do. So this is how you're going to solve problems. You're going to draw the region of the domain in the xy plane. Now, as we said before, there are 2 different ways to make the slices. So first, we can either slice vertically. So notice that when we slice vertically, our widths are little delta x's, or we can slice horizontally. And if we slice horizontally, then each slice has a width of delta y. And then the second step would be to make, in each case, the slices in the other direction, but we don't need that to set up the integral. So we can stop here. So we have to choose one of these two things. So notice that, so let's just look at the first choice. So if we slice vertically, the widths are delta x, and what's the range of x values? The range of x values goes from 0 to 2. Now, what about on each slice? On each slice, what is the range of y values? So on an individual slice, the smallest y value is 0, and on each individual slice, the biggest y value is the function y equals x squared. So the biggest y value is x squared. So that gives us our boundaries for the integral. And now we can write that integral down. So notice that when we did the first slice, we had delta x. So that delta x or dx goes on the outside of our integral. And then our secondary piece was dy. And the boundaries for y were 0 to x squared. That gives us the volume equals integral from 0 to 2, integral from 0 to x squared of our function dy dx. So x has constant boundaries and our outer integral is dx. Y has a variable boundary and the inner integral is dy. Now, alternately, we could have sliced the other way. So what would that look like? So slicing the other way, notice that each slice has a width of delta y, which will become dy, and the slices range from y equals 0 to y equals 4. Those are the boundaries for y. Next, on each slice, what is the possible range of x values? Possible range, notice that the smallest x value comes from the function y equals x squared. And if y equals x squared, that means that x equals the square root of y. So there's your smallest possible value on each slice. And then the biggest possible x value on each slice is 2. So therefore, we get that the boundaries are y goes from 0 to 4, and x goes from y to the 1/2 to 2. And now we can write down the integral to find the volume. Volume equals integral from 0 to 4, integral from y to the 1/2 to 2 of our function, blah, blah, blah. And now it's dx dy. Again, notice that dy is the outer integral with constant boundary 0 to 4, and x is your inner integral with the variable boundary y to the 1/2 to 2. Okay. So once it's set up, how do we then do the calculation? Well, we do the calculation about as you would expect. So let's take a look. So let's look at the first one, the vertical slice, the integral that comes from vertical slice choices. So the volume is this, and now let's do the integral. So let's calculate the inner integral dy. So integrating dy, you get 4x squared y plus 1/4 y to the 4th plus 4/3 x y cubed. And now we need to plug in, evaluate y on the boundaries, y equals 0 to y equals x squared. So plug it in. So plugging that in, you get, looking over here, you get 4x squared times y, but plugging in x squared, that's x squared times x squared, now you just get 4x to the 4th. And then plugging in x squared into the second term, you'll see you get 1/4 x squared to the 4th. That's just x to the 8th. And then 4/3 x times x squared cubed. So that's going to be x to the 6 times x. So you just get 4/3 x to the 7. And then plugging in y equals 0 naturally gives you 0. So I just left that out. Okay. So I hope everyone's following that, because this is the new tricky step where we're plugging in a variable boundary. Then from here, it's old business. We just integrate this with respect to x, which gives you 4/5 x to the 5th, plus 1/36 x to the 9th, plus 1/6 x to the 8th. And then you plug in the boundaries for x, 0 to 2. So doing that, doing the arithmetic, you just get 3,712 over 45, which is approximately 82.49. Okay, now that is calculating the integral as it was set up with vertical slices. What about the other integral? Well, it came from setting up the exact same volume, so hopefully it's going to give us the same answer. Let's take a look. So here was the integral from the horizontal slice choice. Notice that it's dx dy, y goes from 0 to 4, and x goes from y to the 1/2 to 2, integrating our function. So let's do it. Integrating dx gives us, on the inside, 4/3 x cubed plus xy cubed plus 2x squared y squared. And now we're going to plug in x goes from y to the 1/2 to x equals 2. So plug it in, and what do you get? So plugging in x equals 2, we're going to get 4/3 times 2 cubed, which will be 32 over 3. Then you'll get 2 times y cubed, so 2y cubed. And then 2 times 2 squared times y squared. So 8y squared minus, and now we've got to plug in x equals y to the 1/2. So we get 4/3 y to the 1/2 cubed, so 4/3 y to the 3/2, plus y to the 1/2 times y cubed, so that'll be y to the 7/2, plus 2 y to the 1/2 squared times y squared. So that's just going to work out to 2y cubed. And then we subtract. Simplify. Oh yeah, sorry, that is. The only thing that simplifies is the 2y cubes cancel. And then we integrate, and you get this, and now evaluate from y equals 0 to y equals 4. Do the calculation, and you get 3712 over 45. You get the exact same answer. So yes, it's true. You can integrate in either order. Notice now, however, if you want to integrate, if you want to choose an order, dy dx versus dx dy, yes, you can do it. However, you can't just take one integral and just flip the boundaries. Notice how they have notice how the boundaries get set up in very different ways. We're going to talk later on about switching the order of integration in more complicated scenarios. For now, let's just say that given the initial problem, you can choose to set it up either way, either dx dy or dy dx, and in the end, you'll get the same answer. Oops, okay. So when we do this calculation, it may help to have both of these pictures in mind. The one on the left, where you imagine there's a region in the XY plane and then also your function over it. However, you're not going to be graphing that one by hand. So what you'll be graphing by hand to help you sort things out is the one on the right, just a two-dimensional graph of what's going on in the domain in the XY plane. So I just want to mention that we said, hey, you can set this up either way, either dy dx or dx dy. So we chose a fairly simple scenario. It turns out that the fact that going from one to the other, switching the order of integration, turns out to be a deep mathematical theorem. So let me just mention, to be mathematically complete, the fact that you can switch is called Fubini's theorem, which says that if f of xy is a continuous function on the rectangle, so x going from A to B and y going from C to D, then the double integral over the region of f of xy dA can either be written with the integral dx dy or the integral dy dx. Turns out this is surprisingly hard to prove. You wouldn't think it, but it is. And this winds up being true for more general regions, as not just rectangles. But the proof is hard and beyond the scope of this course. Okay. So I want to mention something here. In the beginning, when I said let's talk about how we can conceive of setting up volume integration, what we said is that there's two ways to set it up. We can either think of the problem being written, of the integral being written as dA, or we could set it up with the variables explicitly written out. So either a dx dy or dy dx. So we're going to be seeing both and we're going to be using both. And we're going to talk about how to use those in the coming problems. Okay, so let's see how one of these questions might appear. So here we go. So here, no context, just find the double integral over the region of x plus 2y dA, and then R is this region. It's bounded by y equals 2x squared and y equals x squared plus 1. So how do we do it? So as we've seen in previous problems, the very first thing to do is to draw a graph of the region. That's going to help us sort things out. So what does this look like? So y equals x squared plus 1 is going to be a regular parabola, but translate up 1. And then y equals 2x squared. If you remember, this is just going to be like a skinny parabola, coming from the origin, but a skinny parabola. So something like that. That's not bad. Okay. And here's my region. Okay. So as we saw in the previous case, we now have a choice to make. The choice is which way do we want to, how do we want to set the integral? Dx dy or dy dx? So we have to make a choice. So what do those choices look like? So slicing vertically looks like this, as opposed to slicing horizontally would look like this. Slice, 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 and now we've got a problem. Give or take my amazing drawing skills, the problem that you can see is that when we try to make slices, things go badly. When we try to make horizontal slices, things go badly. So a couple of things go badly. Number one, our slices on top are partly inside the region and outside the region. That's clearly no good. So that makes taking horizontal slices a very bad idea immediately. A second thing to notice is that even the bottom slice, the slices near the bottom, which are totally on the region, they start and end on the same function. So they just start on the negative branch and then they end on the positive branch. So that would be slightly irritating to set up an integral. So for that reason, doing this problem with horizontal slices is probably not optimal, and therefore it makes the most sense to set this problem up using vertical slices. So once we know that, now we just have to set up what the boundaries are. So when we set up our vertical slices, we need to know, first of all, we know that vertical slices, their thickness is a delta x, and we need to know the range of x values because it's not given at all. So in order to find the range of x values, we need to know where does it start, which is over here, and where does it stop for smallest value and largest value. Now, how do we find those 2 points? Those 2 points occur at the intersection. So we need to solve for the intersection. So y equals 2x squared and y equals x squared plus 1. Just plug in and you get 2x squared equals x squared plus 1. X squared equals 1. So very quickly we see that x equals 1 and negative 1. Those are the lower and upper boundaries for x. Okay. So now we can set up our integral. So the double integral over the region of our function x plus 2y dA equals what? So now we know we're making vertical slices. So x gets these constant boundaries of integration. So dx goes on the outside. And the boundaries for x are -1 to 1. Next, the boundaries for y. So looking at the graph, which boundary is the lower boundary? The lower boundary on our region is the skinny parabola. So that was 2x squared. That's the lower boundary. Upper boundary is x squared plus 1. And that is how we set up the integral. Once the integral is set up, the rest is just a pretty straightforward calculation. So first we have to integrate dy. So that gives us xy plus y squared. And now we need to plug in our boundaries, y equals 2x squared to y equals x squared plus 1. So plugging in x squared plus 1, you get x times x squared plus 1 plus x squared plus 1 squared. All of that minus x times 2x squared plus 2x squared squared. We still have our dx integral. So multiplying out gives us this. Simplifying gives us this. So it's the integral from -1 to 1, -3x to the 4th minus x cubed plus 2x squared plus x plus 1. Just got that from a bunch of algebra. Now we integrate dx, which gives you this, -3/5 x to the 5th minus x to the 4th over 4 plus 2 over 3x cubed plus 1/2 x squared plus x, all evaluated as x goes from -1 to 1. Plug it in, do the calculation, and you get 32 over 15. Okay, so there is our first sort of integral from scratch. We have to figure out everything by hand. So I just want to check if there are any questions on that one. Great. Okay. So let's take a look at another integration or volume problem, and let's see how we'd set it up. So here is the function z equals xy. Find the volume under that over the region enclosed by y equals x plus 1 and y squared equals 2x plus 10. Okay, that's definitely a funky one. So let's take a look. So first, to draw the region, just doing a quick sketch. Notice that y equals x plus 1 is going to be just a straight line on slope 1. That's pretty easy. And then what about the second one? Notice that the second one, you can solve it out to get x equals y squared minus 10 over 2. Long story short is that it's going to be a parabola, but a parabola that opens to the right. So just from that quick sketch idea, you can see that the region is going to be the one on the left. Now, as always, we need to make the choice, which way do we slice it, which tells us which order we're going to set up for integration. So vertical slices look like this, and horizontal slices look like this. Now, from the sketch of the two slice choices, which one looks like is going to be easier to use, and why? Well, notice that with vertical slice choices, you've got different functions on top and different functions on bottom at various times. To the left, it's the two branches of the parabola. On the right, it's the positive branch of the parabola over the straight line. With the horizontal slices, you've got the same function always for the lower bound and the same function always for the upper bound. That one is going to be easier to set up. So let's do it. Okay. So when we slice that way, notice that the little width is delta y, which is going to become a dy. That's going to go on the outside. And then we need to find and we'll need to find the boundaries for y. But also we're going to want to find the boundaries for x. So the boundaries for x, solving for x, the lower boundary on the parabola, or sorry, the upper boundary, if you solve for x on the line, x equals y minus 1. And then the lower boundary in the parabola, solving for x equals half y squared minus 5. And then next we need to find the boundaries for y. Those are the constant boundaries. We solve those by finding the intersection. So the intersection is where y minus 1 equals half y squared minus 5. So that just gives you, let's see, putting it all together, y squared minus 2y minus 8 equals 0. And then that's just that's a straightforward quadratic to solve. You factor it and you get the boundaries, y equals -2 and 4. So let's set it up. So the volume, as a general statement, we know it always equals the double integral over the region R of our function f of x, y dA. Now, what does that mean? Well, with the dA, we decided that we're going to do horizontal slices. So dy is on the outside and dx is on the inside. And we just found the boundaries for y are -2 to 4. And we found the boundaries for x are half y squared minus 5 up to y minus 1. And then the function goes in the middle, is what we're integrating. Okay, and then from here on out, it's just a bunch of computation. So I'm going to go through this one fairly quickly. So integrating the function dx, you get half x squared y, plug in, and then you have to evaluate for the boundaries for x, which gives you this. And then sorting out the algebra gives you this expression, and now we have to integrate it with respect to y, which gives you this expression, and then we've got to evaluate on the boundaries. Y goes from -2 to 4. Plugging in gives you blah, 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 all that. And then simplifying gives you 0. How can the volume be 0? Well, technically we are calculating signed volume, just like from single variable calculus, signed area. So remember that you could calculate the integral of a function and get 0 if the positive area and the negative area canceled out. Same thing here. Positive z-values are going to give you positive counting volume. Negative z-values will give you negative counting volume. So we're, in a sense, counting net volume or sign volume might be 0. Hypothetically, if you wanted to count all volume positively, you'd have to do the double integral of the absolute value of the function. For functions of 2 variables, this is incredibly hard to do by hand. So you could do something like use technology for that. Okay. So one last question about how do we set up an integral. So find the double integral over the region of sine of y squared dA, where R is the region bounded by y equals x, y equals 1, x equals 0. So in order to calculate this integral, what's the first thing we have to do? We have to figure out, we're doing the double integral dA of something dA. We have to figure out, do I want this dA to be dx dy, or do I want it to be dy dx? So the first thing we do is we sketch the region and we make slices. So the region, y equals x, y equals 1, x equals 0, just gives us this triangular region. So if we make vertical slices, it looks like the one image, and then the horizontal slices look like the other image. So either form of taking slices looks like it should be fine. Every slice is contained in the region, and in each case, you've always got the same function on top and same function on the bottom for each slice. So let's go ahead. Let's try to do the vertical slice choice. So the vertical slice choice gives us the integral. So vertical slice choice, every width is a delta x, which becomes dx. And x values, here you can see pretty much by inspection. Since x equals 0 and y equals 1, at y equals x, you just get the 0.11. So x goes from 0 to 1. And then dy, the lower y value, y equals x, so the lower y value is x, and the top value is 1. Okay. What is the integral of sine of y squared dy? You might think to do a u sub, but there's no du. Turns out this integral is impossible. So don't try to do it. So it actually turned out to be helpful here that we've got 2 choices for how to set up the integral. So we're not going to use the vertical slice choice because it gives us an integral that's impossible. So instead, we're going to use the horizontal slice choice, remembering that the horizontal slice choice changes the order of integration. So let's see what that does for us. So the horizontal slice choice, notice that each slice, it has a width delta y, which becomes a dy, and the range of values for y goes from 0 to 1. Next, on each slice, lower value for x is 0, upper value is the straight line, which is, so x equals y. So now let's do the integral. So how do we do the integral? Okay. So the integral of sine of y squared dx, well, that whole thing with respect to x is just a constant. So you just get x times sine y squared. And now we evaluate x goes from 0 to y. So plugging in equals, okay, so plugging in when x equals y, you get y sine of y squared minus, well, plugging in x equals 0 will just give you 0, so I'll leave that alone, dy. So now how do we do this integral? Haha, now that the integral has started this way, now we can do a change of variable. So now we have u equals y squared, and then du equals 2y dy, or moving that to the other side, 1/2 du equals y dy. So now we can do the integral. Right. And if u equals y squared, then when y equals 0, then u equals 0, y equals 1, gives us u equals 1. So changing the integral, the boundaries, as we just noticed, actually stay 0 to 1. And now it's the integral of 1/2 sine of u du. And now we just go ahead and do this integral. So this integral is negative 1/2 cosine u, and u goes from 0 to 1. Negative 1/2, oops, sorry. Right, yeah. Cosine of 1 minus negative 1/2 cosine of 0. So that winds up giving us negative 1/2 cos 1 plus 1/2, which, if you're curious, is approximately 0.23. Half cos 1. Okay. Notice that we've got a couple different things that may dictate, when we set up an integral, which way do we want the order to be. So previously, if the boundaries, just to scroll back for a second, if the boundaries of integration are constant, okay, it disappeared. Okay. If the boundaries of integration were constant, we could do the integral in either order. Sorry, it seems to have disappeared. I'm not sure why. Anyway, but we did this calculation out before. We could just switch the order, switch the boundaries because they were constants. It's easy to do. However, if the region is not a rectangle, if your boundaries of integration are not constant, there are a bunch of considerations. Sometimes one slice choice is better than the other slice choice, as we saw here. That will determine how you set up your integral. Sometimes one of the orders of integration gives you an integral that you can do, but one of the other orders you can't do, and that will determine how you want to set up your integral. So there's all these possibilities. Okay. All right. So one more. Now I want to give one more application of what we can use a double integral for, and it's slightly unusual, but let's take a look. So what I want to do right now is take a step back to single variable calculus. So what if we just integrated with no function? So if we just did the integral from a to b of dx, what is that? That would just be x from evaluated from a to b. That would just be b minus a. So what does that tell you? That just gives you the length of the integral, the length of the interval over which you're integrating. Now, if you wrote this out in approximate form, you could think of it as the sum of the delta x's before it becomes the integral of dx. So in other words, you're just adding up all the little lengths. So if you have an integral dx with no function, that's just going to give you the length of a line segment. It's silly, so we never did it, but it's actually, it's a true thing. But now we can bring that back to our two variable situation. So if we do a double integral with no function, just the double integral dx dy or the double integral dA, what we're in essence doing is adding up all the little areas, and that just gives us a total area. So a double integral of no function, just dA, is an area, and it's the area of the region that we're integrating over. So the double integral, so the area equals the double integral over the region dA, or the double integral over the region dx dy. And of course, the boundaries of integration are going to be determined by whatever our region is. So let's take a look. So let's find the area of the rectangle when x goes from -2 to 3 and y goes from 0 to 4. I know, silly question, just to hang with me. We can do this as a double integral. So the area is the double integral over the region dA. So let's set this up. In this case, I'm choosing to set it up dy dx. So y goes from 0 to 4, x goes from -3 to 2. So the integral of dy is just y evaluated from 0 to 4. That just gives us 4. And then the integral from -2 to 3 of 4 dx is just 4x going from -2 to 3, and that gives us 20. Now, of course, another way to do this would be to say, well, if y goes from 0 to 4, we're just talking about the area under the function y equals 4. So we could have just said the area is the integral from -2 to 3 of the function 4 dx. But of course, all this was incredibly silly because it's just a rectangle, and the area is just 4 times the, notice that x goes from -2 to 3, so the width is 5, y goes from 0 to 4, so the height is 4. 4 times 5 is 20. The double integral method was not useful in that case. However, it would be useful if the region is not a rectangle or if it's not defined by a function. For example, find the area enclosed by x plus 9 equals 2y squared and x equals y and above y equals 0. So how would that look? Well, we make our first basic step. We know that the area is just okay. So first, we're going to need to find the intersections. So substituting for, we know that x equals y squared, so substitute for y squared, just x. So x plus 9 equals 2x. That gives us that x equals 9, which gives us the intersection point y equals 3. And we've also been told above y equals 0. So therefore, a boundary is y equals 0. And very briefly, I'm just going to say that we're going to choose to slice horizontally. So dy is on the outside. So therefore, on each slice, x, solving for x in each case, x equals 2y squared minus 9, and x equals y squared. Those are the boundaries for x. So how do we set this up? We know that area is just the double integral over the region of dA. Again, no function. So how do we want to set this up? We've chosen to slice horizontally. I'm skipping a step, sorry about that. And therefore, horizontally, horizontal slices have a width delta y, which becomes dy. The boundaries for y are 0 to 3. The boundaries for x, as we said, 2y squared minus 9 and x squared. And now we just do the calculation. So notice that the region that we've described is a very strange region. It actually looks something like and then 2y squared minus 9. Something like this. And we said above y equals 0. So our region is right in there. So it's a very strange region. But setting up the double integral gives us a nice, clean, straightforward way to find the area of that region. It's not one that you'd want to do using single variable calculus techniques. Okay.